Alrighty, awesome. So I'm here to talk about a rather large topic today, which is graph machine learning for 2024. We only have a half an hour, so there's going to be some things that I'm going to move through rather quickly. But the agenda for today, I want to do an overview of graph machine learning. I'm going to use the acronym GML sort of throughout this presentation. It stands for graph machine learning. I want to talk, this is going to be very forward looking. So I want to talk a lot about where this is all going. And as a hint, it's going to involve generative AI as it's sort of taking everything by storm. We're going to talk about using graph machine learning to enrich a grounding knowledge graph, a knowledge graph used for grounding. And at the end, hopefully we'll have time. I'll do a short demo and kind of show you how some of this stuff works. So to start with the overview, I want to level set. I know everyone here probably already knows what a graph is. But it's basically a data structure that consists of nodes connected by relationships, and databases like ours, like Neo4j, structure and store graph data. And property graphs have a few sort of key components. So the first is nodes, which represent entities. The second are relationships that represent associations or interactions between those entities, right? Entities being things like people, places, things, and relationships being sort of those interactions, people knowing people, people operating vehicles, stuff like that. And properties are attributes of either nodes or relationships. And the great thing about a graph is because it has this very general structure, from an AI perspective, it serves as almost a superset of the different data structures you can use. So relational data, document data, vectors can be stored as attributes inside of knowledge graphs, as well as unstructured data, either through named entity recognition or simply representing unstructured data as vectors. And we'll see that Neo4j has the ability to store and index vectors and do all the stuff with unstructured data, which is great. So that brings us to what graph machine learning is. And it is obviously the application of machine learning to graphs, and specifically for predictive and prescriptive tasks. So this has applications sort of across a wide gamut of use cases, things like recommendations, predicting next best action, identifying fraud patterns, doing entity resolution in customer 360 examples, as well as looking to optimize or find efficiencies in large complex routing networks, logistics, bill of materials, supply chains, things of that nature. And so if we're to think of like what are the technical things that graph machine learning does, there's really two big groups, as is normally with machine learning. We have our supervised machine learning tasks, and this is where we're training on graphs that have labeled data inside of them to make predictions. And there's sort of three big buckets inside of here. And that would be node property prediction, which is a classic example would be things like tagging documents that are related to one each other inside of a graph database, or trying to predict fraud accounts. For example, you might have a banking use case where there's accounts making transactions with each other, and you can use node property prediction to cast predictions that you're interested in about those entities. Link prediction is where you're trying to predict relationships, basically. And this is very useful for things like entity resolution, where you're trying to resolve entities together. Drug discovery also comes up quite often. And recommendations as well, trying to predict kind of what a user might purchase next. And graph property prediction is the last in this group, and that's concerned really with predicting individual graphs. So that comes up a lot in different forms of pharmacology and biology often, where they're sort of modeling molecules. That will come up. And the other side of the coin is unsupervised tasks. And I'm not going to go through every one of these in detail just because of time constraints. But a lot of this boils down to representation learning, which is creating graph embeddings and similar structures, clustering and community detection inside of graphs, so figuring out how things group together, similarity inferences, which is basically trying to predict what nodes might be similar to each other, or where preferences might be in the graph. And then there's other algorithms like centrality and pathfinding that can tell you things about your data and sort of fall under the GML umbrella. And when we think about how to accomplish graph machine learning, sort of the approaches just beyond the task, there's sort of three big buckets here too. And people talk about some of these a lot, some of them more than others. But really it comes down to classic algorithms, which are going to be when people talk about things like PageRank and centrality and Louvain for community detection. There's going to be embeddings, and I'm specifically calling them non-GNN. So these are vector representations of nodes and other entities in the graph, and I'll get to that in a second. And then graph neural networks, which is the neural network architecture that's built for graphs. And I'll talk about that here as we go through the slides. So graph algorithms, like I said, are going to be your pathfinding, your community detection. They have names that are very similar to the tasks that we just went over, because some of them directly solve for those things. So you can use them independently for unsupervised graph machine learning, as well as creating features for downstream machine learning models. So things like risk scoring, creating new centrality metrics and things. These can be very useful for machine learning workflows. And with embeddings, there's lots of different types of embeddings, but I'm going to use a node embedding as a quick example for this, given the time constraints of this presentation. So the idea with graph embeddings, and it's really a nice example to look at node embeddings, is you're trying to take the entities inside of a graph and represent them in a way that's going to be conducive for machine learning models. And so you see a graph over here, and it has things that are grouped together, nodes that are sort of naturally clustered together. If we made a node embedding of them, in this case, I'm making a two-dimensional node embedding. And what happens is we can show these nodes in a two-dimensional plane, and they sort of have the same proximity, right? They sort of group the same way. And so most node embeddings in practice are not going to be two-dimensional. They're going to be hundreds of dimensions or thousands. But this general idea basically allows you to take the complicated graph structure and represent it in this numerical way that serves as great input for machine learning features. So for doing the classification problems, the prediction problems, any type of EDA or clustering, this can be a very helpful metric. And there's other types of embeddings too, such as knowledge graph embeddings and path embeddings. But node embeddings are kind of the most common one that's discussed. And then the last sort of bucket here is graph neural networks. And this is sort of more end-to-end, right? Where a graph is taken as input, and then it uses a neural network architecture. And it's actually making sort of embeddings in a bunch of neural network layers. And then finally sort of learning how to make those embeddings so that it could put it through a final prediction layer. And there's a wide range of use cases for GNN. You might have heard of graph convolutional neural networks, graph SAGE, graph attention networks. So all of these are different sort of flavors of graph neural networks, and they're really designed to be end-to-end. And the only thing that I do want to note on GNNs is that they do have their pros and cons, because they're talked about a lot. They can automatically learn signals in the graph. They're inductive. And they can handle really deep graph structures in theory, but they also tend to be kind of complex. They can be difficult to scale, and they require, in general, a lot of expertise to work with, and they're kind of hard to interpret. So oftentimes they're sold as like the end-all be-all of graph machine learning, but a lot of times for practical use cases, using algorithms and embeddings can yield great results too. So just wanted to mention that really quickly. So I know that was a lot to go over, just to sort of summarize the GML space in 10 minutes. But I do want to talk a little bit about where this is going, and especially relative to generative AI, because a lot of practitioners, right, if you're a developer that's dealt with data science topics, or you do machine learning and you're an engineer, this sort of stuff kind of changes where everything sits, right? Because we're seeing all these advances in the ability to automate tasks, perform summary, do completion, question answering, even generate code. And these models are becoming more and more available to everyone. And so it's a very natural question of, well, when we have these machine learning capabilities that we've been working on, how do they kind of fit into this, right? And it's important to note that there's a lot that generative AI can't do, right? And when we focus in on these weaknesses, a lot of it has to do with things like lack of domain knowledge, having a knowledge cutoff, And ultimately, because they were trained in this self-supervised way on a large amount of data, and the fine-tuning only happens on a very small amount of that data for specific tasks, they don't always get things right. They can hallucinate, and they have all these sort of inconsistent problems that makes them hard to sort of find applications in the enterprise for, let's say. And so something that I know that we're, as a company, Neo4j, is talking about a lot is, right, this concept that there's really two sides to this coin when we think about generative AI applications. We have the modeling side, the large language models, right, the generative AI that has to do specifically with text. And this can do a lot of great things with language and creativity and kind of pulling facts together. But then when we think about reliable enterprise applications, we also are going to need a knowledge graph or some knowledge base, right, that's going to provide facts to that LLM. And this is sort of how we're thinking about getting around these problems, right, of hallucinations and inconsistencies. And retrieval augmented generation is the pattern that tie these two sides of the coins together, which are both very important. And it's this idea, right, that you can have a prompt, and instead of taking that prompt and going directly to an LLM, like consider a user just asking a question like to a chatbot that's powered by an LLM, you can take that prompt and use embedding techniques. And this would be like text and content embedding, not necessarily graph embedding, or a natural language query, or a combination of the two, to do a database search on your specific data that you need to answer this question for your user, right? Like your own enterprise knowledge base, pull those documents out and kind of combine that with the original prompt to then send it to some completion API, which would then create an informed response. And I know we've already had, and we will have, a lot of presentations kind of just around this. We could spend hours just on this. But I want to talk specifically around where graph machine learning fits in, because there's really two places. So when we think about where graph machine learning can fit in, it's either side of this coin, right? There's sort of the in-model enhancement, basically using graph machine learning for language models. And then there's the knowledge graph piece and enriching the knowledge graph with graph machine learning. And I'll talk more about this second one, because as I'll show you in a bit, I think that they're both wonderful, but one is a little bit more accessible right now than the other. So when we talk about graph machine learning, sort of this first side of the coin in the models, there's a lot of research underway that focuses around this. There's a couple models like Grease, LM, and Dragon, which are specifically focused on this. And they sort of have this two-step approach between retrieval and this mechanism that kind of fuses together information from a text prompt and a knowledge graph. And so when we think about retrieval, basically it learns how to do this this retrieval process where it could take a prompt, it could pull sort of a subset out of a knowledge graph, right? And then the second step in these models is, instead of having a normal sort of LLM transformer, like if you called, ChatGPT from OpenAI, they have sort of their own layer on top of it that fuses the information between the knowledge graph and the text. And Grease LM sort of does this with pre-trained language models and GNNs. And then Dragon is a step on top of it that basically is its own foundation model. It trains the model from the ground up, essentially. And there's other work here sort of in this area of graph machine learning and generative AI models. I don't think anything's been published yet, but there's been work announced from Stanford that they're looking into sort of semi-structured knowledge in retrieval, which is basically splitting prompts into subportions for different structured and unstructured tasks, and kind of basically chopping up a prompt and figuring out how to send pieces of the prompt to different models, whether they be for a GNN to pull data, or for to pull text data from. So not a lot of sort of concrete stuff here, a lot of stuff that's kind of in development. And I guess my point overall for graph machine learning within the context of sort of the in-model piece for generative AI is that there's a lot of future potential here. It's something that a lot of people are talking about, and it's very exciting, but it's still very new. And it's not really the most accessible right now. It's not really the easiest model to pull into like a lang chain workflow or an orchestration workflow for building an LLM app today. And so that kind of brings me to the second piece, which is knowledge graph enrichment. And the idea behind this is pretty simple. We know we have a knowledge graph that we're using, or some sort of knowledge base, right, to back our LLM. And so the idea is we want to enhance the graph to enable LLMs not only to use the facts in the graph, but also make intelligent inferences about your enterprise data. So this means using similarity algorithms, for example, in a recommendations graph. So I can make recommendations, real-time recommendations or personalized recommendations inside of a prompt for my application. Also doing things like link prediction to discover missing relationships. So if you have like a medical knowledge base and you want to sort of make a link in between papers or make a link in between drugs to say, hey, these drugs interact with each other, or this drug can be repurposed for this other treatment, right? This other therapeutic treatment. Then now that you have that in your knowledge base, the LLM can take advantage of that and include that in information when it does its retrieval. And there's a ton of other things that you could do with node prediction and community detection and centrality scoring. That graph on the right is an example of a fraud detection graph. And basically, as you enhance the graph, right, and you bring more facts and inferences to light, you can make your LLM responses more relevant. And so I wanted to show you a very quick example of how this can work inside of Neo4j. Before I do that, I want to talk a little bit about graph data science. I know that we have a lot of users that are very familiar with the database itself. Graph database was going over it before, stores things as nodes and relationships. But we also have this other piece called graph data science inside of the database. And basically what that does, it allows you to project the data into a memory efficient format and run machine learning algorithms on them in sort of an optimized way. Basically, you take pieces of the graph and you do aggregations and you put it in a format where you can run graph embeddings really quickly. You can do centrality calculations really quickly. And you can either write that information back to the graph or use it in a downstream model or whatever you like. So there's over 65, I think 70 plus algorithms at this point that can generate insights. So a lot of what I was talking about before, centrality, pathfinding, community detection would be included in this. Being able to engineer graph features for machine learning pipelines. So we have the ability to engineer things like embeddings and other things that you can pipe into your ML ops platform. So say you wanted to take advantage of graph features for doing machine learning for classification, for node prediction, for link prediction. We have sort of very fast data transfer for that. We have our own native ML pipelines as well inside of the platform. And importantly, we have a Python client that allows you to integrate with external machine learning workflows very easily. So very fast data transfer and kind of putting them into data frames and tensors and other objects. So you can do your feature engineering and come back and do EDA and come back. And it just makes it very efficient. So with that said, I want to start with my demo example. I do have a link to the code here. I promise I'll make the READMEs a little bit better as I have a little bit more time. Just got this up today, but this is using H&M, so a retailer. They released a public data set around fashion recommendations. And before doing this presentation, I've gone ahead and loaded a graph. And I will go into Workspace and show you what this graph looks like. So I'm using Aura for this. And let me actually show you this picture here. So this is our schema. And basically, and I know these labels might throw you off a little bit, but this is a graph of a historical graph that's showing you different articles. So these are like articles of clothing. All the clothing are variants of products. So a product would be like a sweater, for example, and then variants would be like different colors of the sweater, right? Or different sizes of them. They all belong to a specific department. So the store has different departments, kind of different sub-brands, and then customers. And so if I were to sort of make sort of a quick query, right, of these pink nodes are customers, and I'll zoom in a little bit more. They have this purchase history that goes back to buying these different products. And then inside of that purchase history, you can see that some customers will be connected. So we start getting this graph of customers being related to each other based on their preferences, right? What they've purchased. And what I've gone ahead and done is for these, there's a text embedding for the products. And basically, this text embedding is created by a transformer model. It's the same sort of model that backs things like ChatGPT, large language models. And this, when I ingested it, I actually used OpenAI to generate these embeddings. And these embeddings are generated on the product descriptions, which if I go all the way down, because I open this up, and I might as well, well, I'll go all the way down. Or well, maybe I can. So, here it is. it's on top, of course. So it's an embedding of the description and some of this other metadata here kind of concatenated together. And those text embeddings will kind of serve as a form of semantic search, right, which is an important part of generative AI. And for this, I'm really going to focus more on the semantic search piece, as putting this in a prompt is just sort of wrapping it around a completion API for LLM. And basically what I want to show you now that I have it loaded is kind of how to use Neo4j to do a few interesting things. So I'll start with just showing you the top of this notebook. So I'll run through here. This Python notebook, basically, all I'm doing is I'm going to connect to Neo4j, and I'm going to load, in this case, an OpenAI embedding model. You're not able to see the environment variable, but I'm going to use OpenAI. And before I even get into anything graph data science, I want to show you a simple vector search. So say, for example, we have a prompt from a user to search for a product, right? Say winter sweater with zipper. So what that's going to look like is if I use OpenAI, it'll give me a text embedding vector. And we have a vector index inside of our product. And what that basically allows you to do, if I run that, it will use that vector index to find semantically similar products to this winter sweater query. So when I go to get the results back, you see that I'll have a scoring of sort of the best results. And you'll see that these descriptions closely match what that user entered, right? And it's not doing any lexical matching. This is just doing matching on sort of here's what's similar, semantically similar to what the user entered. So that by itself is very powerful. But you might want to ask beyond this, right? How do you add other recommendations, either personalized or other things that a user might want to buy, based not on the text data, but on the history and sort of that enterprise specific data that you have, the purchase history and all the connections in there that reveal preferences that are not available inside of this text. And what I'm going to do to reveal that and really scale it is I'm going to walk through a GDS workflow, a graph data science workflow. And this will do graph machine learning. And basically what I'm going to do is I talked about projections a little while ago. I'm going to create a projections with customers, articles, and products, and the purchase relationship, as well as this variant of, which connects the articles and the products. And from there, I am going to create a graph embedding. This is different from a text embedding. This is a graph machine learning embedding. It's a node embedding. And that embedding will tell me sort of how close nodes are together. And if I run them, this is what they look like. They're very similar to the text embeddings, where it's a list of numbers. And then what I'll do is I'll run something called k-nearest neighbor, and I'm running it specifically on the article. So what I'm doing is I'm saying if two articles, but articles are versions of products, are close in the graph, I want you to write a relationship between them that says customers also purchase these things. And what that's going to do is it's going to really help me scale my ability to sort of hop along user preferences. Once that's done, now I can start having a little bit more fun. And this is where I say graph machine learning can help with enrichment of a knowledge graph and how it can help with results. Because say you didn't want to just do that basic search. You wanted to do a recommendation along with that. So you wanted to say, well, given that the user entered or is looking for this winter sweater with a zipper, what else can go with that they might want to purchase, right? And so the answer here, and I'm glad it didn't fail, it'll give me my search results, but then I can say user may also be interested in, and then what it's going to do is it's going to give me things that go with that and some things that are similar. But see, like trousers, like knit trousers, might be something that someone might want to buy with the sweater, right? But semantically, it's not very similar to the original search. But because I've enriched my knowledge graph with machine learning, I'm now able to put in recommendations for things that are not necessarily exactly the same as what the user was looking for, but might go with them, right? And then sort of the layer on top of this is if you wanted to do personalized recommendations. So say you actually know who the customer is. And I can also say sort of a max date for the purchase history. Basically, I'm going to find with this Cypher query their purchase history going back through 2019. And this is a historic data set. So I think it only goes up to like to 2020 or early 2021. And so I can see some of the things this person had purchased. And what I could do is instead of just doing a recommendation off of what everyone, sort of the entire graph kind of, right, what users might also like, is I can take this specific user and I can basically take the intersection between what this query is doing, what they've bought, and the search that they just put in. And when I do that and I run this cell, now what I'll get is I'll get a similar, well, this is all the, sorry, this first part is just the normal search return. These are the personalized recommendations. And now what I'm getting is I'm getting a combination between this is what this person's bought in the past, this is what they're asking for now, and here are some recommendations that are very specific. So sweaters that are very specific to what they've bought in the past, plus the semantic search context. And then you'll see there's actually, I think it was, there's a sweater in here that they bought, which they bought before. But what you'll notice is that a lot of these elements, if I were to go back to the top, would be very similar to what they've purchased before, and then it would give some additional recommendations, basically based on the search prompt. And obviously, some things like a dress or a skirt or other things that might go with the sweater. So that was my very simple demo that I wanted to show you, just to kind of give you an idea of what you can do with knowledge graph enrichment. Obviously, this is just a start. This is just a start, but there's a lot of exciting stuff that we have to do going forward. And I hope that these examples, and especially some of the other examples that you've seen of just getting started with a Gen AI stack, right, and getting that first piece going with the completion API in combination with this stuff can be really helpful. That is everything I have for now. I don't know if there's a Q&A portion to this or not, but I'm happy to take questions now or have any further discussion with the 1 minute we have remaining.